Everything you see, everything you have ever loved, every object you look at in the night sky, including comets, moons, planets and stars, are made of ordinary matter, which consists of only about 5% of the universe, and that's the bit of the universe we understand. The remaining 95%, however, we have no idea what it truly is. But we've given this mystery a name, and we know just about enough that it's two separate things: dark matter and dark energy.
Remember, dark matter is this idea of matter that is out there, we believe, in space. And we come to that conclusion because when we take account of the gravity that can be exerted by the matter that's not dark, which means matter that we can see, gives off light, reflects light, matter of that sort, the amount of gravity that such matter can exert just is not enough to account for the motions that we see through astrophysical measurements, astrophysical data, right? I mean, the analogy that I'd like to use, I think it's a pretty good one. If you have a bicycle wheel that's wet, as it spins, you know that the water droplets fly off as the wheel turns. Similarly, in galaxies that are spinning, if they're spinning at a sufficiently fast rate, stars should be flung outward. And we see galaxies for which the stars should be flung outwards, but they're not, which must mean there's something else out there that's holding those stars inside of those galaxies. The belief is that there's additional matter beyond the matter that we can see with our telescopes, and that dark matter is responsible for the gravitational pull that's keeping those stars from flying outwards like the water droplets. Good, that's dark matter. I should say, there's a lot of dark matter, we think, when you do these calculations. There's on the order of 4 or 5 times as much dark matter as there is ordinary matter, you know, the stuff that we're made of.
It's extremely counterintuitive that the mass majority of energy distribution in the universe is invisible to us, especially when we gaze the night sky and observe trillions of stars, but there could be also stars that are partially made of dark matter. The early universe may have harboured so-called dark stars. These type of cosmic objects would be composed mostly of normal matter, like normal stars, but a high concentration of neutrino dark matter present within them would generate heat via annihilation reactions between the dark matter particles. This heat would prevent such stars from collapsing into the relatively compact and dense sizes of modern stars, and therefore prevent nuclear fusion among the normal matter atoms from being initiated. Under this model, a dark star is predicted to be an enormous cloud of molecular hydrogen and helium ranging between 4 and 2,000 astronomical units in diameter, and with a surface temperature and luminosity low enough that the emitted radiation will be invisible to the naked eye. In the unlikely event that dark stars are endured to the modern era, they will be detectable by their emissions of gamma rays, neutrinos and antimatter, and would be associated with clouds of cold molecular hydrogen gas that normally would not harbour such energetic, extreme and rare particles. The other invisible dark stuff that comprises the majority of energy distribution in the universe is called dark energy. The unknown form of energy that affects the universe on the largest scales was observed for its existence from measurements and supernovas, which showed that the universe does not expand at the constant rate. Rather, the universe's expansion is accelerating. Understanding the universe's evolution requires knowledge of its starting conditions and composition. Before these observations, scientists thought all forms of matter and energy in the universe would only cause the expansion to slow down over time. Far from it. Dark energy is accelerating the expansion, but we cannot see it. How can scientists be certain it exists?
Dark energies, in terms of the energy mass budget of the universe, is even more substantial. On the order of 70% of the mass energy of the universe is this dark energy. Dark energy is a different beast. Dark energy, the most convincing evidence for it are these observations of the accelerated expansion of space. Space is not only getting larger over time. That was a shock. That was the shock that initially was really confirmed through the observations of Edwin Hubble. But not only is the universe getting bigger, it's getting bigger at an accelerated clip. So the expansion is speeding up. How can expansion speed up? Galaxies, they pull on each other with the force of gravity. Force of gravity we usually think of as pulling things inward, but yet something's pushing outward. And the remarkable thing is that in Albert Einstein's general theory of relativity, gravity can actually be repulsive. It can push outward, not if the source of that gravity is a clump like a star, a clump like a galaxy, a clump like a planet. Rather, if there's a diffuse energy that is spread uniformly throughout a region of space, then under modest assumptions, it will give rise to a repulsive push, an outward push that can drive the expansion of space to accelerate. And because this energy does not itself give off light, we call it dark energy.
The evidence for dark energy is indirect, but it comes from three independent sources. Distance measurements and their relation to redshift, which suggests the universe has expanded more in the latter half of its life. The theoretical need for a type of additional energy that is not matter or dark matter to form the observationally flat universe, and measures of large-scale wave patterns of mass density in the universe. Measurements of cosmic microwave background anisotropies indicate that the universe is close to flat. For the shape of the universe to be flat, the mass energy density of the universe must be equal to the critical density. The total amount of matter in the universe, including mesons and dark matter, as measured from the CMB spectrum, accounts for only about 30% of the critical density. This implies the existence of an additional form of energy to account for the remaining 70%. Work from the Planck spacecraft observations of the CMB estimates a universe made up of 68.3% dark energy, 26.8% dark matter, and 4.9% ordinary matter. Researchers have come up with a variety of hypotheses to explain this mysterious force, with unknown properties. Among the populars is the modification of the prevailing theory of gravity, which is general relativity. With the field of gravity, there is a field of theoretical physics that seeks to describe gravity according to the principles of quantum mechanics, where quantum effects cannot be ignored, such as in the vicinity of the black holes or neutron stars. This field is called quantum gravity. In theories of quantum gravity, the graviton is a hypothetical quantum of gravity, an elementary particle that mediates the force of gravitational interaction.
In the quantum mechanical framework, the forces that influence how things move, the electromagnetic force, the nuclear forces, they're all part of the standard model of particle physics, which envisions that those forces are indeed communicated by a particle. For the electromagnetic force, photons, nuclear forces, W and Z bosons, and so forth. Now, gravity is a force of nature as well. Einstein tells us that gravity is associated with space-time. The geometrical structure of space-time determines the gravitational influence that a body moving through that region of space-time will experience. Now, if you believe, as most of us do, that quantum mechanics and general relativity have got to come together, then the paradigm of a force being communicated by a particle will spill over to the gravitational influence as well, and that gives rise to this notion of gravitons. No one has ever seen a graviton. We're not surprised by that. It's the smallest packet of the weakest of nature's forces, so it's not as though we have expected to see it lighting up our detectors, and it hasn't, so not a mystery. But if this idea is true, then you can actually think of the fabric of space, which is the medium of gravity, as being a whole huge collection of gravitons that are arranged in a coherent pattern that manifests on large scales as the geometry of space-time, but on small scales would have this distinct particulate quantum mechanical description.
There is no complete quantum field theory of gravitons due to an outstanding mathematical problem with renormalization in general relativity. If gravitons exist, they're expected to be massless because the gravitational force has a very long range and appears to propagate at the speed of light. In string theory, believed to be a consistent theory of quantum gravity, the graviton is a massless state of a fundamental string. But we will discuss that more extensively in another video. Thanks for watching. Did you like this video? Then show your support by subscribing and ringing the bell to never miss videos like this.